So the very first thing on your notes sheet that we want to make sure that you're aware of is that a sequence is nothing more than an ordered progression of numbers. So it has a definite order to it, and it's a listing of numbers. We denote a sequence by using the curly brackets. We surround it with curly brackets. And there are two types of sequences. One of them is called a finite sequence, which means that it stops, it ends. And the second one is called an infinite sequence because it goes on forever. We denote an infinite sequence by the ... after one of the numbers. It says continue in like manner. So we have two ways that we can name a sequence. One of them is an explicit notation, and the other one is a recursive formula. Okay? The explicit is a lot like a formula. You plug in numbers and you get output. In goes the input, out comes the output. Recursive is based on the previous things that you had, the previous numbers. So let's talk about explicit first. So as I mentioned, it's like a formula. You plug in integers, so we're never going to deal with negative numbers or usually positive integers. We won't be dealing with fractions or decimals or irrational numbers and so forth. And we plug those positive integers in to generate the sequence. So we want to know what are the first four terms of a sub n equals n squared plus 1. So when we write a sub 1, all we're doing is we're talking about the first term. Okay, that's the way to write, or that stands for the first term. Okay, so that first term, the n is replaced by the number 1, right? So what will we get if we replace every n by a 1 and evaluate? 2. Yep, 1 squared is 1, 1 plus 1 is 2. So our first term is 2. Unless they tell us otherwise, you're going to start with 1. Okay, somewhere in your directions it will say let your first term be, or start your sequence with letting n be 0. But for the most part, unless they say otherwise, start with 1. Okay? Then a sub 2, the second term. What's the second term going to be? Good. Why? Yep, 2 squared is 4, 4 plus 1 is 5. Third term? Good. Because 3 squared is 9, and 9 plus 1 is 10. And then the fourth term? Because 4 squared is 16, and 16 plus 1 is 17. Okay? Not too hard, right? We're just following a pattern using a formula. The second type of sequence is called a recursive sequence. And that is found, has two parts. You always start with the first term, and then you may have more than one term given, but for the most part we start with the first term, and then we have a rule that tells how the next terms are built upon the previous terms. Okay? So we're told that b sub 1, our first term for this particular sequence, they decided to name it b instead of a, is negative 10. Okay, so we immediately know b sub 1 is negative 10. Now, here's our formula, or our pattern, or our rule for it. So when we want the second term, when we want b sub 2, we're going to take b sub 2 minus 1 and add 5 to it. What is 2 minus 1? And b sub 1 stood for what? So we're going to take a negative 10 and we're going to add on 5. And what do we get? Negative 5. B sub 3 is nothing more than b sub 2 minus 5, or plus 5. What was b sub 2? So negative 5 plus 5 is? And what's b sub 4 going to be? Good, because we just keep adding 5, don't we? That's a recursive formula based on the previous term, right? And the first term has to be told, has to be named, listed. Questions on this slide? Okay, next. We want the explicit definition. Everyone see where we're at on this paper in the upper right? Explicit definition for the nth term. And we're given two different sequences. The first one starts with 1, 5, 9, 13, and 17. So what do you notice? We add 4 each time. So the recursive formula is actually easier to write than the explicit one. The recursive formula says that we have to tell what the first one is, right? First term. So if you want to call it A or B, it doesn't matter. But the first term is 1. And what do we do to get the next term? Add 1. So we take the previous term and we add 4. Someone said add 4, right? Every time we add 4. Because if we put the first term in there, it's 1, right? The second term, A sub 2, will be A sub 2 minus 1, or A sub 1, the first term, and add 4. So 1 plus 4 gets us 5. The third term is going to be the second term plus 5, or 4 again. So 5 plus 4 gets us 9. So recursive was easier, right? Okay, this was our definition for recursive. But explicit is a little tougher. Okay, with this particular problem, we're adding 4 to each time, right? So let's think about what this would look like if we graphed it. Running out of space. Okay, when we're talking about our first term, right? First term, we got 1. Second term, we got 5. Third term, we're getting, manage my board very well here. Third term, we're getting 9, right? What does that look like? I did it well. Like a line, right? It's supposed to look like a line if I had graph paper. Kind of looked at exponential. Okay. What's my slope of this line? Four over 1, right? Our slope is 1, or is 4. 4 over 1. And what would our y-intercept be? When we would be at 0, one step away, our 0 term would be -3. So our b would be -3. So we could rewrite this this explicit formula as a sub n is equal to 4 n plus b, right? Or -3, or 4n minus 3. Let's see if that works. First term, when we plug in 1, do we get 1? Second term, when we plug in 2, do we get 5? Third term, when we plug in 3, do we get 9? Yep, so it works. Okay? So the explicit one's a little harder to generate, and we'll talk more about those tomorrow. I want you to see them so you know where they come from, but for the most part, you're doing the opposite. We're giving you the explicit form and asking you to come up with the sequence. Not giving you the sequence and asking you to come up with the form. Okay? Letter B. What do you notice about our terms of that sequence? See lots of 5s, right? 5's in the denominator. Okay? In fact, this first one is 1/5, right? The second one is 1/5 to the second power, right? 1, 5 times 5 times 5, right? So what would our explicit form of this be? So we want it to be to the bottom, okay? So 5 to the negative n power. Would that work? 5 to the negative 1 when it is 1. 5 to the negative 1 is 1/5. When n is 2, 5 to the negative 2 is 1/25. 5 to the negative 3, 1/125. That's perfect. Okay? Now, if someone else had said a sub n is equal to 1/5 to the n power, would that be okay? Or 1/5 to the n would also be okay. So there's not going to be one unique explicit formula for this. Do we want to come up with a recursive? No? Okay. We don't have to because we're not going to focus on that today. We will focus on it tomorrow and Monday. Okay? Questions on this one? All right, next. So you remember good old factorial from last year, right? Factorial, I think, last year was the first time you were probably exposed to it. Maybe you saw it before that. So if I want to find 5 factorial, what do I do? What does factorial mean? Almost. Not adding. Multiplying. Yep. 5 times 4 times 3 times 2 times 1. Okay? Our book's going to define it as 1 times 2 times 3 times 4 times 5. I prefer to see it the other way. 5 times 4 times 3 times 2 times 1. Okay? And there's a reason for that. So let's take 5 times 4 times 3 times 2 times 1. If you have a graphing calculator and you want to know how to do it, I saw some of you pulling out your calculator, figuring it out already. You type a 5, and then you choose the math button. There's a math button, and you arrow over to probability, and then you either press 4 or arrow down to 4 and press enter. And everybody get 120? Okay. So this was 5 times 4 times 3 times 2 times 1, and it's 120. Because 20 times 3 is 60 times 2 is 120. I think often, because this is buried, it's faster to do it without the calculator. Everybody get 120 on their calculator? Okay. So let's look at this one. We have 8 factorial divided by 2 factorial times 6 factorial. So this is going to be, nope. So it's going to be 8 times 7 times 6 times 5 times 4 times, right? So this is the 6 factorial. You're going the other way, okay? And then here's our 6 factorial again, right? And then a 2 times a 1. So these cancel, right? What's 8 divided by 2? What's 4 times 7? Because I'm lazy and don't want to write it. Once we see the 6 factorial down here, we can stop and cancel, okay? I'm lazy. I don't want to write it all. Okay? Absolutely. By all means, save the pencil lead. Save the time. Okay? I think it's faster. Okay? I'll erase you, Caleb. I'll erase you. Not there yet, right? You're blank? Ready? Yep. Ready, set, go. Do you see why it's faster in most cases? Because those buttons are hidden. They're not easy to find. Okay? So your keystrokes aren't going to save you. You can check yourself, right? Check your answer to make sure it's right. But you're better off to likely do it this way. Yes. Mm-hmm. Exactly. Yep. Okay. Feel good about those? Okay. So this is the kind of factorial you'll see on the ACT or the SAT to make sure you have good critical thinking skills and you really know what it means. Okay? Not quite. It's not just one. Okay? I'll show you the lazy method. That's fine. But what does n plus 1 factorial mean? Not quite. What did 8 factorial mean? Okay? So and so forth, right? Okay? Everybody good with that? And we keep going, right? We don't know how big n is, so we have to keep going until we get down to 1. Okay? Now, what's n factorial? We went 8 and then 7, right? So n minus 1, n minus 2, until we get down to 1, right? It's just n plus 1. Okay? Make sense? Everybody feel good about that one? Yep. Yep. Once you figure it out, you don't need to write it all out. Okay? Mm-hmm. Okay. All right. Questions on this one? Okay, here we go. Next one. Thank you. Okay, now here's a special case. I forgot to mention it. Okay? Justin saved me from forgetting to say this. We have a special case. 0 factorial is defined as 1. Okay, so if you ever end up with a 0 factorial, just remember it's 1. Okay? 0 times anything is 0, right? But we got beyond that, so we just said, hey, back it up, back up the truck. We're just going to call it 1. Okay? Make sense? Not really, probably, but accept it. Okay? All right, here we go. Series. A series is next. So our sequence was an ordered progression of numbers, often surrounded by curly brackets, right? A series is nothing more than the sum of a sequence. A sum of a sequence. Okay? So we are going to use something called summation notation. And summation notation is just a way to write a series. We use the letter, is it Greek or is it Latin? Greek? The Greek letter sigma. The Greek letter sigma to denote a summation. Okay? And the variable that they're using, whichever it happens to be, it's often I, it could be n, it could be k, is called the index. N is the upper limit, 1 was the lower limit. Okay? So we have two kinds of series. One of them is called a finite series. It's also known as an nth partial sum. Okay? A finite series means that we have a sequence that is ends. And we're adding up all the terms from the beginning to the end. An nth partial sum means we may have an infinite sequence, but we only want the 7 terms, the sum of the first 7, or the sum of the first 20, or the sum of the first 5. Okay, that's our nth partial sum. Our 20th, our 7th, our 5th partial sum. Okay? An infinite sequence is one that goes on and on and on forever. So if we're finding the series for an infinite sequence, we had better hope that it's converging on a specific number. Okay, or we'll be here forever. Okay? We won't ask you for it unless it's converging on a number. Okay, so let's find the sum. Now, our book does a better job with their typography than Microsoft Word does. I haven't figured out how to make it look right. Okay, in your book, it's going to look like this. Sigma I equals 1, 5. And then 3I. So that's what your book is going to look like. It's basically our typography in Word does not want us to put them above and below the sigma. Okay? So we are going to add up how many numbers? 5. Okay? What will the first number be? 3 times 1. So the first number, if I plug 1 in for every I see, is 3. Right? The second one is 6. The third one, and then the fourth one, and the fifth one. Okay? So when we add those numbers up, what do we get? 45. Okay? 3 and 6 is 9. 9 and 9 is 18. 18 and 12 is 40, and 30, and 30 and 15 is 45. Okay? So a series is nothing more than a sum of a sequence. Question? Great question. Okay, so when we wanted our first term, we're plugging in 1 for I. So that means that we're taking 3 times 1 and getting 3. And then when we let I be 2, we're taking 3 times 2 and getting 6. Yep. You start by counting with 1 and then go to 2, then because they have an upper limit. Yep. So they give you a lower limit and an upper limit. You just apply the formula, generate your terms, and add them. Exactly. So sequences and series aren't hard. Okay? Especially when you're going from given the formula and asked to apply. Okay? All right, next one. Find the series when k is 3 to 6 of 1 plus k squared. K is going from 3 to 6, and I want you to find 1 plus k squared. Perfect. Good. Yep. So 10, 17, 26, 37. Because everywhere we see a k, we have to plug in whatever number we're on. Our first term we were looking at was the third, or k equals 3. So 1 plus 3 squared. Then our next term was 4, so 1 plus 4 squared. And our next term was 5, so 1 plus 5 squared. And then we were up to 6, 1 plus 6 squared. Order of operations says square first and then add. Square first, add, square first, add, square first, add, sum them up. Okay? Next one is an infinite series. Okay? But we get a stop as soon as we notice a pattern. Okay? So I is going from 1 to infinity, and we're told to take 3 divided by 10 to the I power. So for our first term, we're taking 3 divided by 10 to the first. 3 divided by 10 is what? 0.3, 3/10, right? Okay, so that's 0.3. When I is 2, 3 divided by 10 to the second. 3 over 100. What's 3 over 100? 0.03. And then plus 0.003. Okay, so it'll be 0.3333333, right? So what is that converging on? What number is this? 1/3. Okay, we can have an infinite number of 3's after it, right? But that will converge on the number 1/3. Questions on this one? All right, let's talk graphing calculator process and then assignment. Okay, so on your graphing calculator, I think I showed you it before. Sometimes it's faster to do these without the graphing calculator, right? But there will be some that are pretty awful in your assignment. So for the most part, you can do these by hand or with your regular calculator functions. But there will be 2 problems on your assignment that ask you to use a graphing calculator. Okay, if you don't have one, you'll be working with some not so nice numbers. Okay, all right, so we're going to find that same one that we did just a moment ago, 90. Okay, to do that, I want you to press second stat. It's near, I don't have mine with me, to get to the list area. And then go over to math and choose 5, which is the sum. We're taking the sum of a series. So second stat, over to math, down to sum. And it wants to know, what are you summing up? We're summing up. We have to go to second stat. And we go over to ops for operations. And we want to sequence number 5. And now we're putting in our stuff. Okay, this was 1 plus x squared or 1 plus k squared in our example. We don't have to use that specific variable. We can use any variable. So we put in 1 plus, the x is the xt theta n button on your calculator if you want to use that shortcut. And then you use your squared key. If you have a older style calculator that doesn't give you the whole menu, you want to put a comma next. The commas are above the 7. Okay, the variable is x, so you will put the 1 plus x squared comma x, or arrow down and press x if you have a newer style calculator. Then it wants to know the start or the lower limit. So if you're doing them all in one nice neat line, you push a comma 3 and then an upper limit comma 6, or you can use start at 3, end at 6. Your step is going to default to 1 unless you tell it otherwise. So you just go down and press paste or press enter, depending on which style of calculator you have. And you should have something that looks like the little thing on your handout. And when you press enter, you should get 90. So the expression is 1 plus x squared. Okay, yours is a little different. It's a different version. Okay, everybody get 90? All right. To my knowledge, unless Mr. Clemenger and I decide otherwise, we didn't have any restrictions on the test last year as far as what kind of calculator to use. So you will have the use of a graphing calculator. Okay, unless I tell you otherwise. You don't need a graphing calculator. We always try to write it so that you don't have to. You need a scientific, but not a graphing. But I would prefer that you did have a graphing, especially if you're going into math, and so forth. Okay, so, all right, assignment. Let me give you the assignment.